Hello students, welcome to Memoneet. I am Sakti Swarup, teacher of Memoneet. I am here to start off with a new portion of electrostatics, that is electric potential energy and electric potential. Okay, so this we are preparing for the BTS test series part 2. If you don't know the BTS test series, this is Brahmastra test series, and this test series will contain the only every single sort of question will be asked, that is from the NCERT only, nothing beyond the NCERT. Okay, so please do enroll and prepare well for the test series. Okay, and this test series also follows the current NTA pattern, so we expect that this test series will help you in NEET 2025 examination. Potential energy. Electrostatic potential energy of a point charge at a point in a electric field is the work done in taking the charge from the reference point, generally at infinity, to that point without acceleration. So what it says, that let's say we have source charge here. This is the source charge, and we have the test charge as at infinity. This is the test charge at infinity. So this states that when you are taking the test charge to one point, okay, to one point in the presence of of external electric field, in presence of external electric field, we have to do some work. So this work is stored in the form of electrostatic potential energy. Okay, and this will be done with zero acceleration. So the charge is taken with zero acceleration. Okay, so let's say we have the electric potential energy, it is del U, so that is equals to U final minus U initial. This will be equals to the work done in presence of the work done by the external electric field. Okay, so W external, so we know that the external external work done is equals to, that is of U conservative, okay, minus of the conservative potential, negative of the conservative work done. Okay, work done by the external agent is equals to negative of the work done by the conservative force. Okay, so this will be equals to minus of integration of f dot ds. Okay, this is why we know that work done is equals to f dot ds. Okay, f dot ds integration, so work done by the external agent is equals to minus of f dot ds is equals to minus of work done by the conservative force. This force is which force? That is conservative force. Okay, so force is equals to k q1 into q2 upon x square. So what what will be the work done? That is W is equals to k q1 q2 upon x square dx. Okay, f dot dx is the force, its integration. Okay, will be equals to k q1 q2 upon k q1 q2 into is whole into minus of 1 by x. This is minus of 1 by x minus of 1 upon x, that is from let's say we are taking it from r1 to r2. Okay, so this will be equals to k q1 into q2 upon whole into 1 upon, this is from r1 to r2. Okay, so 1 upon r1 minus 1 upon r2. Okay, so this is what, this is work done by the electrostatic force, and we know that the electrostatic force is also a conservative force. Okay, so in the very first lecture I have told you, so the potential energy we can write it as del U is equals to minus of K Q1 Q2 whole into 1 upon R1 minus 1 upon R2. Okay. So this is the potential energy. How we will represent that? We can write it as also U final minus U initial. We can write it as U final minus U initial. Electric potential energy of a system. Let's say we have a charge here, that is, here is positive charge, here is another positive charge, and here is another positive charge. First charge, this is second charge, and this is third charge. Okay, so let's say first charge we have it here. Okay, and at initial condition the second charge is at infinity and the third charge will be at infinity. So when we pick up the second charge and travel it to here, okay, place it here, then a potential energy must have generated. So we can write it as U12. Okay, so when we are placing the third charge here, then it is U13. Okay, and when we are placing the when we are placing 2 and 3 at this position, there must be potential energy generated within these two charges. So this will be U23. Okay, so potential energy of system tells that the sum of all the potential energy that is placed here. Okay, the work done by the external agent against the internal agent to make a system here. Okay, so here the potential energy, we know that between the two charges, let's say this will be in form of triangle and the distance is L. Okay, here L, here L, and here is also L. Electric potential energy, the net, will be defined as U12 plus U13 plus U23. Okay, because this potential energy, when we are placing 1 and 2 together, and this is for the 1 and 3 and between the interaction between the 2 and 3 also. So for 1, 2, what we will write? The potential energy for external agent. Okay, we have potential energy, that is K Q1 Q2 upon X. Okay, and when the potential energy against the external agent, that is for the conservative force or electrostatics work done, then the potential energy will be equals to K Q1 Q2 upon X, that will be in negative. Okay, so this is equals to, let's say it is Q1, this is Q2, and this is Q3. Okay, so K Q1 Q3 upon Q2 upon L plus K Q2 into Q3, sorry, it is K Q1 into Q3 upon L plus, then for the third one, that is K Q2 Q3 upon L. So this is the net potential energy of the system of the charges here. Guys, let's say we have positive charge here, here another positive charge, here another positive charge, and here another positive charge. These are placed in the form of sphere. Okay, in the sides of the sphere. Okay, and sphere have side A, here A, and here it is A. So the potential energy will be, this is 1, this is 2, this is 3, and this is 4, which have all the charge Q. Okay, okay, these are all are the charges present here are Q. Okay, so we have potential energy net is equals to the interaction of potential energy between 1 and 2 plus U 1 and 3 plus U 1 and 4. Okay, and then for the second set we have U21 which is already done here, then U23 plus U24. Okay, 24, then plus U31, it is done here, U32 which is done here. Okay, and potential energy between the interaction of 3 and 4 charge, third and fourth charge, U34, and the fourth one, it is already completed everything. Okay, so we don't have to repeat anyone. Okay, so here this is for the U potential energy between the interaction of 1 and 2 second charge, first and second charge, we have k q1, sorry, k q into q upon s a. Then for the u13, that is k q into q upon, what is the distance here? Okay, what is the distance here? This is under root 2a, because this is the diagonal, so under root 2a plus then u1 and 4, that is equals to k q upon a, then u2 and 3. Okay, this is equals to 2 and 3, then k q into q upon a, then u2 and 4. 2 and 4 also, this is the diagonal, so we can write u2 4, that is k q upon under root 2a. Then last one, that is u3 and 4. Okay, so this is u3 and 4, that is k q upon a. Okay, this is a is the distance between 3 and 4, third and fourth corner. So all the sum will be the potential energy of the system. So potential energy of the system will be 1 2 3 4. We have 4 k q upon a into 4 plus 2 into k q upon under root 2a. Okay, so this is the final answer for this question. Let's see another question here. We have three equal charges q are placed at the corners of the equilateral triangle of A. Find out the potential energy of the charge system. So here it is a corner, B corner, C corner, A, B, C, and we have three equal charges q, q, and q. So u of the system, potential energy of the system, we can write it as interaction between A and B plus u, B and C plus u, A and C. Okay, so this is equals to k q upon, what is the side, A plus k q upon A plus k q upon A. So this will be equals to 3 k q square upon A. So this is for the first bit. Calculate the work required to decrease the side of triangle to a by 2. Okay, let's say we are making it a by 2. The sides will be a by 2. So the work required, W, is equals to, it is the external work, so we can write u final minus u initial. So u final will be 3 k q square upon a by 2 square, sorry, a by 2, it is not square, it is a by 2 minus 3 k q square upon a. So this will be equals to 6 k q square upon a minus 3 k q square upon a, that will be equals to 3 k q square upon a. Now let's see the third question, that is, if the charges are released from the shown position and each of them has same mass, then find the speed of each particle when they lie in the triangle of 2A. Okay, so when they are released from the triangle A, okay, when they have side A, when they are released, the only force that will act, that is electrostatic force. Electrostatic force. Okay, so the work done by the electrostatic is must be equals to the change in the kinetic energy. Okay, so work done by electrostatic, we know that u, the negative of potential energy, it means u initial minus of u final, that is equals to k final minus k initial. Okay, and k initial, we know that we are releasing it, it means the k initial is 0. Okay, so this will be equals to u initial, we have k q square upon a into 3 minus of u final, when we have side 2a, that is 3 k q square upon 2a is equals to half m v square into 3. Okay, because 3, why we are writing, because we have to find out the kinetic energy of the whole, it means 3 charges, so we have 3 kinetic energy, that is half mv square. So this will be equals to 6, this is equals to, we have 2a 6 k q square minus 3 k q square is equals to 3 upon 2 m v square. Okay, So this will be equals to 3k q square upon 2a is equals to 3 upon 2 m v square. So 3 upon 2, 3 upon 2 cancelled out, and the velocity is equals to k q square upon a m into a. So this under it. So this is the velocity of the particle. Okay. Energy density, that is we have energy density formula, that is equals to half epsilon e square. E is the electric field here, electric field, and epsilon is the permittivity. Okay. So epsilon we can write for the different medium. We have epsilon naught into epsilon r. Epsilon r is the relative permittivity in other medium. Okay. Epsilon naught is the permittivity at in the air or the free space. Relation between electric field intensity and electric potential. Let's say we have uniform electric field. These are the uniform electric field here. Okay, and we have to find out the potential from point A to point B. Okay, we'll write VB minus VA is equals to E dot dr. Okay, uh, only E dot dr. It is minus of E into the distance between the A and B. Okay, and as E vector dot AB vector. Okay, this is the distance between A and B. So when we are putting in the non-uniform electric field, we have, let's say, Ex. Ex is equals to the electric field when represented is as the electric potential. We have E vector is equals to the negative gradient of the potential, that is minus of dV upon del V upon del X. So when we are writing Ey, okay, so this will be minus of d del V upon del Y. Okay, when we are writing as Ez, okay, that is equals to del V upon del Z. Write E net is equals to Ex I cap plus Ey j cap, this is vector, okay, plus Ez k cap. Okay, so now what we will write, minus of del V upon del X I cap plus minus of del V upon del Y j cap plus minus of del V upon del Z k cap. Okay. So now look here, if electric potential and electric field depends only on one coordinate. Okay, so let's say we have E vector is equals to minus of del V upon del X. Okay, so here we can write also minus of del V is equals to E vector dot dx. Okay, so the del V is equals to minus of E vector dot del x. Okay, so on integrating both the sides, we have the V2 minus of V1 is equals to minus of integration of E dot dx. Okay, this is how we can form the electric potential from electric field. Okay, in this question here, the electric field is equals to 2x I cap plus 3y j cap. Okay, so the electric field will be equals to the minus of del V upon del x. So del V is equals to minus of E dot dx integration. So on integrating this, so the del have here, it is minus of E dot dx integration and plus minus of E dot dy integration. Okay, so this will be equals to V2 minus V1 is integration. Okay, V2 minus V1 is equals to minus of E dot dx. Minus of electric field is for the x coordinate is 2x dx. So 2x square upon 2. If we integrate dx x, we have x square upon 2. Okay, so minus of 3y square upon 2. So in this we have V2 minus of V1, that is origin, at origin it is 5, is equals to, when minus if we take it common, so 2 x sorry, it is x square only. 2 is cancelled out. It is x square minus 3 y square upon 2. Potential V2 we can write it as minus of x square minus 3 y square upon 2 plus 5. So this is the answer. Potential. Let's say we have charge here, the source charge here, and some other charge which is infinity, and we are taking it to some position here. Okay. So when we are taking it from the infinity to this point, okay, we have to do some work against the external electric field. Okay, external electric field by taking the charge or the kinetic energy of charge as constant. Kinetic energy of charge will be constant. So this work done uh, in against the external electric field is the electric potential. So electric potential V is equals to W external upon Q. We can write it as, and this will be equals to work done by the electrostatic force, which is the conservative force upon Q. Okay, sorry, it is minus of work done. Potential is a scalar quantity. This is a scalar quantity, and it can be positive, negative, or zero also. This is SI unit. SI unit is joule. V is equals to joule per coulomb, or we can write it as volt. Okay. Due to the point charge, let's say we have positive charge here, and in this point we have to find out the potential. So we can write potential is equals to W work done upon Q. Okay. So work done is equals to uh, the F dot ds. Okay. We have, that is force due to the electrostatic force, that is minus of F electrostatic dot ds upon Q. Okay. So electrostatic force we can write it as minus of Q into E dot ds upon Q. Okay. So this we have, that is equals to minus of E dot ds. Okay. So electric field due to the point charge we have kq upon x square. Okay. Dot dx. Okay. And it will be in minus, negative. Okay. So minus of kq whole into 1 upon x square. If we differentiate it, it is minus of 1 by x. So this will be equals to kq upon x. So if I am talking that that is it is the charge here, and we have to find out the potential at point P, which is at distance x. So potential is equals to kq upon x. Okay. The question over here, we have 2 point charges as situated at this point and this point. Find out the potential at point C. Okay, we have the graph here, and the A is present minus 2 comma 0. Okay. This is the A, that is minus 2 and 0. Okay. Then B is present at 2 and 0. 2 meter and 0. Here it is B. And C we have 4 and 0. Okay. This is C, that is 4 comma 0. Okay. And D is present 0 under root 5. 0 under root 5. Okay. So here if we find the potential at C, and the 2 point charges at situated at point A and B, that is here 2 microcoulomb and here it is minus 4 microcoulomb. So we have the potential, we will write kq upon x. Okay. The distance from the A and C is from here from the origin to A it is 2 meter, and from the origin to the point C, that is 4 meter. So we can directly write K, the charge here it is 2 microcoulomb upon 6 meter. Okay, 6 plus from B we have K into 4 microcoulomb upon, what is the distance between B and C, that is here 2 meter and here it is 4 meter. We have distance that is 2 meter. So here the potential is equals to k 2 plus it is if we equate the denominator, that is into 3 here, into 3 here. Okay, so we have 2 plus 4 into 3 12, that is 14 k upon 6 m. Okay, so this is the value of potential. In the place of k we can put, that is 9 into 10 to the power 9, and we have to solve it. Okay, likewise you can find the value at d. It is your homework for this. So find out the value at potential at d. Okay, at the center of the it is uniform, it is uniform charge ring. Okay, let's say we have here the charge ring, and we have to find out the potential at this point. Here electric field is what? Electric field is 0. It means the potential must be constant at each and every position in between this. Okay, in between this. So we have potential is equals to kq upon r. At any position, let's say this position, the potential is this much. If r is the, here r is the radius of the ring. Okay, we have the non-uniform charge ring. Let's say this is the ring here, and here the charge is distributed as non-uniform. So the potential we can write, that is k q total upon r. R is the radius of the ring. Due to half ring at the center, let's say this is the half ring here, and we have charge present as q. Okay, so the potential is equals to v is equals to kq upon r. Okay, r is the radius of the half ring. Okay, and potential at the axis of the ring, let's say this is the this is the axis here, and we have to find out the potential here. Let's say this is the x distance from the axis, this point. Okay, so the potential is equals to v, and the radius here is okay, v is equals to kq upon r square plus x square root. Okay, what is the electric field we have find out in the second lecture? So do you remember it? It is E is equals to kqx upon r square plus x square whole to the power 3 by 2. So please do revise these formulas, because you have to just put the formulas and get the answer. So do revise this formula every time. Okay, due to the uniformly charged disk, so potential V is equals to, let's say we have disk here it is the disk. Okay, and if we find out the potential here, potential for at point something, let's say it is x. Okay, this point is b and the distance is x here. So we have upon 2 epsilon naught whole into r square plus x square under root minus, okay, this is the potential. So do you know the electric field? If I have not covered this portion, so you can directly only read the formula here, sigma upon 2 epsilon naught whole into 1 upon x minus 1 upon x square plus r square under root. Okay, this is the formula for the electric field, and this is the formula for the potential for the uniformly charged disk. Potential due to uniformly charged spherical cell. We have the spherical cell here. Okay, and this is of radius capital R. Okay, and we have the charge present at the surface of the cell. Okay, charge must reside at the surface of the cell, because inside this there will be no charge, because this is empty space. Okay, so k at outside, let's say this position, the resistance is r. Okay, at point P. So potential, we can find out the potential in the 3 points, that is when the value of r is greater than capital R, or the radius of the cell. Okay, we have potential here, V is equals to k q upon r, which is the distance from the center of the cell to the point P. Okay, and then if we find the value, that is r is equals to r, that is equal to the radius of the cell, we have potential is equals to kq upon capital R. When the radius is r is less than r, okay, when the when the distance is less than radius of the cell, let's say at this point, we will find here, if we will draw one cell and one imaginary cell, then we contain no charge, but after that we are containing charge, so the potential will be k 0 upon small r plus k q upon capital R. Okay, so this will be equals to k q upon capital R, where capital R is the radius of the cell. So these are the three conditions you have to remember. Then potential difference. Potential difference between 2 points A and B is the work done by the external agent against electric field in taking a unit positive charge from A to B without acceleration or keeping kinetic energy constant. Okay, so potential energy we can write it as the V2 minus V1 is equals to work done by the external force, okay, upon Q. Okay, this will be equals to work done by the electrostatic force, sorry, minus of work done of the electrostatic force upon Q. So this we can write, we know that work done is the force into displacement, and force of the electrostatic is equals to Q into electric field. So we can write Q into electric field dot ds upon Q. Okay, so this Q cancelled out, we can write that is E dot ds. Okay, this will be integration. So V2 minus V1 is equals to minus of integration of E dot ds. Okay, potential difference in uniform electric field. Potential difference in uniform electric field, let's say this is the uniform electric field and we have to find out the potential difference from VA to VB. Okay, so VB minus VA is equals to minus of E dot, okay, this is point A and this is point B, E into the distance AB vector. Okay, this is how we can find out the potential difference in the uniform electric field. Potential difference due to long wear. Okay, long wear, this is long wear. So we have for the long wear, this is the wear, and we know that electric field we can write here E is equals to k lambda upon r. This is sorry, let's say we are taking it as x. Okay, this is x, the distance, perpendicular distance from the point as x, k lambda upon x sine theta 1 plus sine theta 2. Here the theta 1 is 90 degree, as I have discussed earlier, because due to the long wear we are assuming that they will meet at something at infinity, and this will be the angle, that is 90 degree will be the angle. Likewise, when we are joining this bottommost position, so this will be the angle, that is 90 degree, this will be also 90 degree. So sine 90 is 1, so we have 2k lambda upon x. So for the electric field we know that 2k lambda upon x. So for the potential V is equals to, we have E dot dx integration, so this will be equals to 2k minus of 2k lambda upon x integration dot dlx. Okay, so we have that is equals to 1 upon x integration is ln x, so minus of 2k lambda ln x. Okay, so this is, if we take it as from x1 to x2, so we have x1 here and x2 here. Final expression is 2k lambda ln x2 upon x1. So this is how we can write the potential difference due to the long wear. Potential difference due to infinitely long sheet. Let's say we have sheet here. Okay, this is the sheet, and we have to find out the electric field at this position. So E is equal to sigma upon 2 epsilon naught. We know this. So potential difference V2 minus V1 is equals to minus of E dot dx. Okay, so we have minus of E dot dx integration. Okay, so sigma upon 2 epsilon naught dot del x integration. So this is equals to minus of sigma x upon to epsilon naught. So this is how we can find the potential difference due to the sheet. Say equipotential surface. If the potential of a surface, imaginary or physically existing, is same throughout the such surface, is known as equipotential surface. So what does it mean? Let's say we have here a circle where in the circle at each position the potential is equal. Okay, here the potential, let's say it is kq upon r. It has charge q and the radius is r. Okay, kq upon r, here it is also kq upon r, here it is also kq. At each and every point in the circle we have the potential that is kq upon r, and it is same throughout the region. Okay, so this is known as the this is what we call as the equipotential surface, because they have the equal potential throughout its surface. So when a charge is shifted from one point to another point on an equivalent surface, then the work done against electrostatic force is zero. This is why, let's say we have the potential here is kq upon r. Okay, here, okay, let's say the potential at position A is kq upon r, and at position B it is also kq upon r. Okay, sorry, is kq upon r. So work done, what it says, the work done is equals to q into v2 minus v1. Okay, so we can also write that is change in potential difference is equals to minus of work done by the electrostatic force upon q. Okay, in the condition, let's see, the potential of v1, that is at initial position, that is at point A, is kq upon r, and the v2, that is at point B, that is also kq upon r. So if we have the difference here, the difference will come to be 0. So work done of electrostatic will be 0. Work done by the external agent will be 0. Okay, so the electric field is always perpendicular to the equipotential surface. Let's say we have surface here, and the electric field, how it will look like, it will always be perpendicular. It will like this. Okay, it will like this. Then this one, this is the electric field lines, and it is always perpendicular. It is always perpendicular. Let's we have a square here. The electric field will be always perpendicular. Okay, for the equipotential surface. So two equipotent surface does not cross each other. If they will cross each other, then it will have two electric field lines, so which is not possible. So two equipotential surface will never cross each other. Okay, with this we complete our third lecture of electrostatics, that is electric potential and electric potential energy. So stay tuned for the fourth lecture. But before I will leave this lecture, so I just want to advise you, try to find out the question related to this and solve it out. And if you have any kind of doubt, please do ask me. Okay, and try to solve the NTA PIQs question, because from this question a major questions, lot of questions will come. Okay, so I will practice those type of questions in the for the BPT 3 test series. Okay, sorry, BTS 3 test series. So don't worry, I will try to figure it out. Okay, so if you want any kind of lecture regarding the question only, so I can also help you. So please stay tuned, and please, if you want anything else from me, you can directly contact me from the Telegram group. Okay, also you can contact me from the WhatsApp group also. Okay, thank you, bye.